Why do perfumes smell different from the sum of their parts? Perfumers will tell you that every perfume mixture is so chemically complex that it often behaves unpredictably. Certainly, odor mixtures do not behave additively. Additively means that you should be able to calculate what the sum of components will smell like from putting together its individual compounds. In reality, you may put a small drop of a compound into a mix and it changes the fragrance of the entire mix in an instant, often in an unpredicted way. The opposite can also happen. You may put lots and lots of a compound into a mixture and it doesn't change the overall fragrance one bit. Scientists refer to these phenomena as enhancement and suppression effects. Specific odor notes of chemical compounds are either enhanced or suppressed when they occur in a mixture. What causes enhancement and suppression effects? The explanation lies in biochemistry. When chemicals enter the nose and reach the epithelium tissue, they activate receptors. Here come the important questions. Which and how many receptor cells do single compounds activate? And when that compound is mixed together with other compounds, do the same receptors react? A team of scientists used a neuroimaging tool called SCAPE microscopy to find out. SCAPE stands for Swept Confocally Aligned Planar Excitation. The scientists exposed epithelial tissues of genetically engineered mice to two mixtures, each consisting of three compounds. They tested how the cells responded to each compound when administered individually, in pairs, and then in the three-part mixture. They found that two things happened. The first effect they observed is suppression. Some cells responded to the individual compounds and some pairs, but showed little response when exposed to the three-part mixture. The reason behind this is called an antagonistic effect, where one compound can block receptor cells such that they won't respond, or respond with reduced activity, to other compounds. In other words, this compound is blocked from reaching the receptor cells by other compounds. Such antagonistic interactions explain why the odor quality of a compound can get lost in a mixture. The second effect is enhancement. Some cells did not respond to individual compounds, but became active when exposed to the mixture. In other words, these cells would only react to compounds in combination, but not to them individually. This is caused by allosteric effect. Allosteric means that a receptor has a site that does not activate the receptor, yet changes the receptor's conformation. When a compound binds to the allosteric site on a receptor, the binding site changes conformation. The receptor now responds to compounds to which it was previously unresponsive. This discovery of antagonistic and allosteric effects can now explain on a molecular level what perfumers have known from experience for a long time. Smells don't simply add up in mixtures. You might be wondering, why do receptors in the human body do this? One benefit of enhancing or suppressing different components of a mixture is increasing the dynamic range of the sensory system. If responses to individual odors generate an expected identifiable odor-specific code, then a simple summation of the codes of multiple odors as present in a perfume blend could quickly fill up receptors. This effect could make numerous mixtures of different odors indistinguishable from one another. In contrast, suppression and enhancement make small changes in the combined code, which gives specificity to the combined code for the mixture. In some cases, these effects may interfere with the ability to identify every odor component within a blend, but would instead provide the mixture with a recognizable identity. What's so special about enhancement and suppression effects? In other sensory systems in humans, such as sight, touch, and hearing, we have not found cases of a stimulus activating one receptor and inhibiting another. In these systems, complex interactions among stimuli occur at higher levels of processing, such as in the brain. Smell is unusual in using stimulus-induced complex activity, starting at the level of primary sensory receptors in the nose. Indeed, perfumery is both an art and a science. Next time you spray on your favorite perfume, you can thank the biochemistry going on in your nose for giving you the perfect fragrance.